Okay, this is a chemistry video, and it is going to finish up for us chapter 11, and it will deal with polarity of molecules. This is actually perhaps the most important thing for us about the shape of a molecule is something called the polarity of a molecule. You will remember back that bonds can be polar. And the way that a bond is polar is if the electronegativity difference is greater than 0.4, greater than or equal to 0.4. You're going to need, for tonight's assignment, the table in your book off of page 334. That's where we got our electronegativities. Now, bonds can be polar, but so can an entire molecule. So let me review. Polarity means that we have opposite ends. Molecules, because they are shapes, have ends to them. And our question will be, are the ends opposite? Do they have opposite charges? Now, at first, you might say, well, this isn't going to be any more difficult than this, and for most of you, that was a simple assignment. But there is a part of this that takes a little bit of thinking as we do it. So I have models of the three different basic electron arrangements. If you remember, electron arrangement was how many electron pairs are around the atom. And an electron pair is a bonded pair or an unshared pair. This is a model of carbon dioxide. I'm going to put that right here, carbon dioxide. If I drew the Lewis structure, and you're going to be asked to do this evening, the Lewis structure will look like this. Double bond here, or you can draw that this way. The electron arrangement, this would be a linear molecule, and the molecular structure is linear. And for those of you who've forgotten, the electron arrangement, we don't take into account the ends. The ends, anything that's bonded, is part of the molecular structure. Now, this molecule has two ends. This end and this end. This is called the middle. If I was to take and bring this at you this way, that end is coming towards you. If I bring it to you this way, this end. If I bring it to you this way, all three of those are coming at the same time. And because of that, this side along here is not an end. These are the ends. If I was to take carbon dioxide, carbon is 2.5, 3.5, 3.5. If I was to mark this, this would be partially negative, partially negative. This is a non-polar molecule. Why? Because the ends are not opposite. You say, but it's different from this. Yes, but if I was to say, what is this end? This is negative, this is negative. Two negative ends are not opposite ends. And so the electronegativity difference happens to be 1.0, but the polarity, this is called non-polar. By the way, what's going to happen is, in order to have a polar molecule, two conditions have to be met. First, the bonds must be polar. And second, the bonds must be polar, and the geometry must have opposite ends that have different charges. By charges, I mean partially positive, partially negative. Okay? So let me take you to a second one. This is a model of sulfur trioxide. This would be SO3. And by the way, you're going to do a worksheet, and it's arranged like this. If we did this, I'm going to skip the dots for right now. The Lewis structure looks like this. It is a double bond. Maybe you can see that. Single, single. This has 3 pairs of electrons, and we would then call this trigonal planar. And this one, the molecular structure, is 3 ends trigonal planar. The electronegativity difference here, sulfur is also 2.5. So this is 2.5, 3.5. So just like this one, partially negative, partially negative, partially negative. So there are polar bonds on this. But once again, if I was to take this and ask how many ends does this molecule have? This is an end, this is an end, this is an end. This is not an end. Say, well, what if you came this way? Well, if I came this way, I sometimes like to think of it this way. If I was to put this into a package, into a box, the box would look like this. Didn't do that big enough. Box would look like this. There's my molecule. This end is negative. This is negative. This is negative. This whole side essentially is negative. So is this and so is this. No matter which way this comes at you, it's a negative end that's coming towards you. And so our electronegativity 1.0, nonpolar. Notice it's not enough to have polar bonds. We have to have a polar geometry. Right? So let me go on to another one. Let's say that we had CCl4. Oops, that one's bad. CCl4. And the electron arrangement would be like this. Chlorine, I believe, is 3.0. Carbon is 2.5. So this is 2.5, 3.0. That's just slightly polar, but even so, it's partially negative, 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 negative. This has 4 electrons, so it's called tetrahedral. And because it has 4 atoms on the end, it's also tetrahedral. We have a electronegativity difference of 0.5, which is polar. But like the other one, if I was to ask you, how many ends does this have? It has 1, 2, 3, 4 ends, and all 4 ends are negative. And as a result, there are not opposite ends to this molecule, and this molecule would be called nonpolar. Okay? But what would happen if I took one of these off? For instance, if this instead of CCl4 was NCl3, oops, should have done that over here. CCl4, NCl3. If you have NCl3, that's nitrogen, and this would be our electron configuration. This is still, because we're counting these, this is tetrahedral, but this is trigonal pyramidal. And by the way, N is 3.0, and chlorine, I'm going to have to make this fluorine here. NF3, make this F, F, and F. The bond, this is 3.0 and 4.0, so this is partially negative, partially negative, partially negative, partially positive. And as a result, we have an electronegativity difference of 1.0. But now, I want you to look at this molecule, not this, just the, in fact, I'm going to hold it right there so you don't hardly even see that. How many ends does this molecule have? Well, 1, 2, 3, and I'm going to take that off, 4. In a sense, it's no different than when this one was up here. There's 4 ends. There are 4 ends. This end, this end, this end, and this end. 3 of those ends are negative. The 4th end is positive. In other words, I could have this come at you this way, or this way, or this way, or this way. When it comes any one of those other 3 ways, it's a negative coming towards you. This end of the molecule is positive. And so this molecule is polar. It's polar. If you thought about this molecule, if we actually have it drawn out, where we have fluorine, fluorine, fluorine. This whole end here is, if I was to draw this, it would be a shape that would be something like this. This is positive end, this is the negative end down here. All right, and then there is only one other possibility. And unfortunately, I'm kind of ran out of room, so I'm going to pull this one off. That's the NF. Let's do water, H2O. H2O is oxygen with hydrogen on two sides and two unpaired. As a result, it is tetrahedral, but we would call this a V-shaped, or I actually like bent better. It's a bent molecule. And by the way, this is 2.1 and this is 3.5, I believe. 3.5. And so this is very, very polar, partially positive, and this is partially negative. Now, the way it's drawn here, it looks like, oh, I have a positive end, this is nonpolar. But not when we take and examine the molecule itself. If I pull this off, and again, don't worry about your the toothpicks there. Your molecule will actually end up looking something like this. Let me take those off because we're actually looking at the atoms. How many ends does this molecule have? Well, this is like a triangle. A triangle has 3 ends. 1, 2, 3. 2 of them are negative. 1 of them is positive. If this comes at you this way, it's negative. If it comes at you this way, it's negative. But if it comes at you this way, it is positive. And backwards. Positive, positive comes at you this way, it is negative. And as a result, this has an electronegativity difference of 1.4, and this would be a polar molecule. Now, I mentioned both of these have to be the way it is. Both of those have to be true. What you're going to find is linear molecules generally are nonpolar, although I want to show you 2 quick exceptions. An exception to that, if you had carbon monoxide, CO, that's our molecule. Now, this is 2.5 and 3.5, that's a linear molecule, partially negative, or partially positive, partially negative. That essentially would be this with a triple bond, and it obviously would have a positive end and a negative end. So a linear molecule can be polar or nonpolar. Trigonal planar is almost always going to be nonpolar. There would be some exceptions, but I'd have to show those to you. That won't be in your homework. Tetrahedral is the same thing. It's these 2 down here that really are the ones we're watching for. They tend to have what we would call as polar geometries. But let me show you one interesting one and then we'll be done. I did NCl3, which would look like that. So this is nitrogen trichloride. This would be tetrahedral, trigonal pyramidal. This trigonal pyramidal, when you draw it, it's that one that has the 3 ends to it. So it's the one that's a tripod that looks like this, and we'd look at that and we'd say, oh, it's got a polar geometry. It's got an end down here that's different from the end up here. Unfortunately, chlorine is 3.0 and nitrogen is 3.0. What's our electronegativity difference? Well, the electronegativity difference here is 0. So even though it has the right shape for a polar molecule, it is considered to be nonpolar. Okay. I have a handout for you, and the handout is, it's a page. It'll be a document that's linked, and it will be molecular polarity handout or something like that. You'll see it. Well, let's just mark it down. It'll be molecular polarity handout. And I do have an answer key for you, but I want to hold off on the answer key until you've tried it. So once people have started doing the assignment, I will, when I send you back and say, oh, you had problems with this, I will send back an answer key so that you can look at it. So this is sort of the conclusion, but what we're going to find is when we get to liquids, next section, when we talk about solutions, we have a real important phrase called like dissolves like. Polar molecules will dissolve in other polar molecules. Nonpolar molecules will dissolve in nonpolar, but polar and nonpolar won't dissolve. This is why we would say oil and water don't mix. Oil is a nonpolar molecule, water is a polar molecule. Pour them together, it's like salad dressing, oil and vinegar. Vinegar is polar, oil is nonpolar, they won't mix. So that actually becomes important for what we do down the road, but this will be, this is what your handout is going to look like. And we'll talk about that as well during class time tomorrow, and I will record that as well. So, all right, that finishes this video.